Newton's first law. It says that any body continues to be in state of rest or uniform motion along a straight line unless an external force is applied. This law at first appears to be counterintuitive. You might easily accept that a body at rest will always remain at rest until a force is acted upon it, but you don't see any body in continuous state of uniform motion. In real life, when you slide a block on the ground, it moves a certain distance and then stops. Newton's first law states that this block should have continued to be moving with same velocity forever until a force is applied on it. In this case, that external force is friction. If you had a smoother surface, the block would have moved even further. On a frictionless surface, the block would have continued to move forever until an external force is applied on it. This property of a body, by virtue of which it resists any change in its state of motion, that is, change in its state of rest or of uniform velocity, is called inertia. Any body having some mass will have inertia and would resist any change in its state of motion. Momentum. This is a new quantity we will learn before we go into quantitatively defining what is force. A big truck moving on road looks more scary than a bicycle moving with the same velocity. That's because truck has a greater momentum, mass being a scalar quantity and velocity being a vector quantity. Their product, that is momentum, is a vector quantity and its direction is same as that of velocity. Now, why is momentum important? Imagine you are hit by a ball. During the collision, the ball applies a force on you. If we qualitatively try to compare this force for various situations, we may start understanding a bit about force. You can feel that a heavier ball will cause more pain during collision than a lighter ball, and a ball moving with slower pace will cause less pain than one moving with higher speed. So we can say that ball with a higher mass has got higher momentum and a ball with lower velocity has lower momentum. The ball stops after collision, hence the final momentum becomes zero. Change in momentum, which is initial momentum in this case, is called impulse. Impulse is also a vector quantity like momentum. Same principle holds when you try to catch a moving ball. If you have played cricket or ever tried to catch a ball, you know it might hurt if you try to catch a fast moving ball abruptly. A more experienced fielder drags his hand in the direction of velocity of the ball and delays the time the ball takes to stop in this hand. We can visualize that a ball stopping abruptly in our hand will cause more pain than if we drag our hand and let the ball slow down over a large time interval. Hence, force experienced by our hand is not only dependent on the impulse, that is the change in momentum of the ball, but also the time for which the impulse is spread. Impulse spread over a small time interval exerts more force on our hand. This is also known as impulsive force. And impulse spread over large time interval reduces the force on our hand. This brings us to Newton's second law, which quantifies force. It says force is change in momentum over a period of time. When we catch a ball, it stops at our hand. Hence, the exact magnitude of force experienced by our hand is impact, which is change in momentum divided by time interval. Greater the change in momentum, more force has to be applied. Shorter the time interval, again more force has to be applied.